Yeah, so thanks very much for coming. This has been a good NDC so far. I've not come this far in the world before. I'm from the UK, so geez, that's a long way to come. So I'm going to talk today about how you can build a robot arm and then use C# and Blazor and SignalR and a couple of other bits to control it. So a tiny little bit about me. I'm a freelance IoT consultant. I'm in the UK normally, which actually plays a little tiny part in this. There'll be a guessing game for you in a bit later on. I'm also a Microsoft certified trainer and an Azure MVP, a Pluralsight author, and I run a bunch of meetups as well, so I like to keep myself busy. I've got 2 little girls at home, and so that's inspired me to become a STEM ambassador and a code club organizer, because I like to make sure that there's facilities there for everybody to learn this sort of stuff. So yeah, that's about me. So we'll talk a little bit about .NET 6. I mean, we're almost out of date already because it won't be long before .NET 7, but you know, .NET 7 not quite ready, not baked yet. We'll then talk about how you can get .NET 6 installed on your Raspberry Pi, and then we'll do a little bit about GPIO, general purpose input-output, and then we'll do what is Hello World, but for IoT. And then after that, we'll look at how we can use other people's code to control some of the electronics that we've got on the desk over here. And then we'll look a bit about Blazor and SignalR. And then moving on, we'll do some final demos. There's a lot of demos in this talk, and so there's a lot of times that this can go wrong. Just keep laughing, it's all good. And then we'll get some Q&A, but I know we're a little bit late, so hopefully we'll get right for that. So .NET 6, I'm not going to blather on too much about this, but it's great. It works everywhere now. Everywhere from the desktop through web and all the way through to IoT stuff over there on the right-hand side, which is great for us when we're programming stuff like a Raspberry Pi. It's got ARM64 support now, which I'm not making use of. It was pretty hard to get .NET installed on an ARM64 base machine, but now we have that support. And we've also got .NET MAUI, which my friend Cliff loves, to be able to make multi-platform apps, which is cool. Global usings, file scope namespaces, HTTP3, record structs, async main, which is cool. I've only used a couple of those, but they're always improving, which is pretty cool. This is a pretty old slide now, but the part I like is that 40% of new .NET devs are students, which is awesome. And certainly from a STEM ambassador point of view, there's a bit less Python and C sitting around in schools, but a little bit more .NET, which is great because a lot of devs just come out of university and they've only done Python and C and stick them straight into .NET and they don't know where they are. So I think that's pretty cool. So, Raspberry Pi, getting that installed is quite hard actually. There's quite a few steps, but I've made a single line install script which goes through all of the steps you can see in that GIF there. And then you just reboot your Pi and you're off and running. The script will install the runtime and the SDK so that you can build on the Pi as well. I wouldn't recommend you do that. You can, but the Pi is not the fastest machine in the world. You should be using a machine that's got, you know, a decent processor in it rather than the Pi's little processor. But it's not too bad, it works, and you'll see that's what I'm doing here just to keep it simple. .NET 6 and GPIO. This thing is basically a NuGet package that allows you to interact with the GPIO on the Raspberry Pi, and I'll dig into GPIO and what that does in a bit more detail going forwards. But this NuGet package not only supports the Raspberry Pi, it also supports a few other boards, but just use the Raspberry Pi. It's a nice machine, assuming you can get one without swapping a kidney for one at the minute. It supports Linux and Windows 10 IoT. Windows 10 IoT really isn't a thing anymore. It was Microsoft's way of getting WPF onto a Pi, and it wasn't very good, and it's barely supported. And there's platforms like the Uno platform now that will allow you to be able to run GUIs on the Pi using WPF XAML, essentially. So that's cool. And you can install that just like any other NuGet package. This is what the GPIO looks like. So this is general purpose input-output. And it's got a bunch of different uses, essentially. So, I mean, controlling things like LEDs or reading things like buttons. But there's also serial ports on there and PWM, or pulse width modulation ports. If we zoom in a little bit more, you can see there's a couple of those there. So you can see the BCM 14 and 15 has got TXD and RXD, so that's a serial port. And then there's a PWM 0 at the bottom of that. We'll be making use of PWM when we go forwards in these demos. There's two different numbering schemes that you can see on there as well. These numbers closest to the pins, that's called the board numbering scheme. And then these numbers, that's the BCM numbering scheme, don't use it. If you use that, now you're having to convert between the BCM numbering scheme and the pin numbering, the board numbering scheme, and just, it's, yeah, a waste of your own energy. But that'll be important. You'll see that in the code in a bit. We'll start off with a hello world for IoT, and that's always flashing an LED. If you've ever done IoT, that's what you will have done first. And the next is always reading a button. And then once you've done that, you can move on. And it's nearly always a temperature sensor, which is really boring. Don't do that. Just hook it straight up to Azure and do something interesting after that. So just to give you a little bit of depth on the circuit, we've got one side of a resistor connected up here to pin 10, and the other side of the LED that's connected to the resistor down to ground. So any IoT devs here, why is the resistor there? Good, yeah, otherwise you'll just, well, there's a couple of different things that could happen. One, you could just blow the LED up, which would be nice. Or the other one is that you blow the Pi up, which would be not nice. Because like I said, they're worth more than your car now. Then on here we've got one side of a button connected to the button, and then the other side is connected down to ground. Now there's something missing from this, and maybe the chap who answered about the LED might spot what's missing. Not so much. I don't do any of that. Normally what you'd have to have is a resistor pulling that side of the button up to a known value. These are what's called open collector inputs and outputs. So when you set it to be an input, it just floats around. I want you to do something with me. And that doesn't, by the looks of it. So if you're doing this with an Arduino, you'll likely need a resistor pulling that up to a high value. And then when you press the button, you'll see it's connected to ground, and that goes low. In the Pi, we've got internal pull-up resistors, so we could turn them on, and you'll see that in the code. But it does make the code seem a little bit backwards in that when you press the button, it goes low, which is false, and if you don't press it, it's high. So you'll see in the code, it feels like it's a little bit backwards. I have got Irish heritage, just so that you know. So let's make that work. So I've got all of my electronics all set up on here. Some of you might be able to see that, but I've also got a camera set up as well. So everybody should be able to see it. So I'll look at the code first, and then I'll run it. Is that big enough, or do you want it bigger? Bigger. Is that all right? I don't go too big, because you got 3 characters on the screen. Is that all right for everyone? Happy days. Go away. So this is just a console application, so there's nothing particularly complicated about it. We're pulling in that device.gpio NuGet package that I mentioned there before, and we're doing threading because I need a delay. So I always leave this console right line hello world in there. You'll see that when you create a new console application generally. But you'll see, particularly in the next demo, it can be quite useful. Certainly if you're building on the Pi, it can take a while and you just don't know when it's done. So always having something that says, I'm ready, is a good thing. Next up, we create a GPIO controller to be able to interface with our general purpose input-output. And then you'll see just here that we've got the pin numbering scheme of board, which is what I was mentioning earlier. You could use BCM, but you're mental if you do. So don't do that. Next, we define our pin connected to the LED. And if you remember, that was pin 10. And then we've got a variable we're going to use for a delay. Next up, we open that pin, and we open it in output mode because we're going to be driving the LED. And we define that against that pin that we defined up there. And then next, I've just got an infinite loop, and I write to that pin a value of high, and then I just wait for that 300 milliseconds, and I write a value low, and then wait for 300 milliseconds and keep doing that. Why do you think I need the delay? Otherwise, it's just going to be half on, half off, and you'll really just see a kind of half bright LED, and that's boring. So, and after that, always make sure you close your pins. The garbage collector will do that for you as well, but it's just good practice. Certainly, if you're controlling things like servos, they get kind of locked into a position, which you'll see in a bit. So the code's pretty simple. There's not much to it. There's only a few lines, but this says only hello world after all. So I've dialed into my Pi on the left-hand side, and you should be able to see the robot arm and an LED just here. And assuming none of the wires have fallen out, which they did the last time I did this, all I should be able to do is just run that. And then wait. Ordinarily, you wouldn't be doing this because now it's building on the Pi. You'd just send the executable down and run that. But now we can see, if I zoom in a little bit down here, we've got a flashing LED. So this is what's called time to flash. How long does it take you to actually, write some code and get this thing to flash? It's actually quite a long time on a Raspberry Pi. Does anybody know why it's quite a long time on a Raspberry Pi compared to something like, say, an Arduino? So a Raspberry Pi is a full computer. It's got an operating system. So you've got to get that put onto an SD card, and then you've got to update it. That takes probably longer than it does to put it on the SD card itself. And then you've got to install, with my single line script, the .NET runtime, and then you've got to write your code and do it. With an Arduino, you write all that code on your PC, plug your Arduino in and flash the microcontroller on the Arduino, and you're off and running. So there's a difference. And the reason I point that out is that this isn't always going to be the best way you do your IoT projects. If you want to do C# on microcontrollers, you can. You can use something called the .NET Nano framework, which folks like Jose Samoes have created, and that's C# for microcontrollers. And it works really well. So there's always a balance. It just depends on how much processing power you need. If you want to do AI at the edge and you're not buying a specific AI microcontroller, then this is going to work really well. If you're flashing an LED and reading a button and things like that, just use an Arduino. It's really going to be up to the particular project you're going to be working on. And the Raspberry Pi is an open source project as well, so you can take this and make your own projects from that as well. So you don't need to necessarily stick with theirs, but geez, man, try and get the chips. That's not easy. So we'll move on. Before I do that, I'll stop my code. So I am not going to do any live coding because I'm nowhere near brave enough. So I'm just going to switch through GitHub branches to get this done. There's enough demos, never mind live coding. So the next one, I'm just going to read the button and flash the LED. So it's not going to get particularly more complicated. Everything at the top is exactly the same. Scrolling down, we've got a new little variable we've created, button pin on 26, and you'll see that's what we've got there. And then we open that button pin, and here is where we're using that input pull-up, if you remember me mentioning before. So don't forget to do that if you're going to make a circuit like that, otherwise it may work, or the temperature might change in your room, and then suddenly it won't work. And you'll wonder why you're going mad. So that's what that is. And then I've got my same while loop, and I use the controller and I read the state of the button pin. And if that's false, if that's low, then I write a value of high to my LED. So this is where it's a bit backwards, because we're connecting that pin to ground when we press that button. And then if we're not pressing the button, we turn the LED off. And then here's where I start getting sloppy, because I'm only closing the LED pin. Really, I should be closing the button pin as well, but you get the idea. It's all good. So let's run that one. And these are two important steps, because you really want to know that you can write stuff out and read stuff back in again. And this is generally what any tutorial will take you through. And it really is a good idea, because it gives you the confidence to be able to carry on, use the rest of the GPIO, and you're off and running. You can see here on the left-hand side, I've got that hello world that I mentioned as well. So, yeah, you don't need to read the stuff that's on that left-hand side, it's fine. So, if I zoom in again, press my button, you should see an LED. That's a really, really complicated and expensive way to connect a button to an LED. But it works. So we're reading inputs and we're writing outputs. We've got the confidence now. We can carry on and do more magical things after that. So let's do that. Let's talk about that sort of stuff. Let's just stop this first. So what you don't want to be doing is writing all of your own code. Somebody's done this for you already. And so we have this device bindings NuGet package. And it's great, actually. IoT devs are geeks. They're probably the biggest geeks out of all of the devs. And so we love connecting to stuff like this and making it work. So this particular NuGet package has got, I think, maybe 35 different devices that somebody's written code for. Some of them are relatively simple, some of them not so much, some quite complicated. But your next project, even though I've told you not to, will likely be a temperature and humidity sensor. Nearly always is. Geez, man, that's a boring demo. Oh, it's 24 degrees in here. That's not going to change unless I start blowing on my temperature sensor and wait for that to change. It's boring. But you can. If there's not enough I/O, GPIO on your Pi, you can use expanders like this. They'll use a serial port to be able to communicate both of these. There's an Explorer hat and a Sense hat. So these are hardware attached on top, little boards that you can plug into the top, and they'll do extra functions. That Sense hat is quite cool because there's 2 of those attached to 2 Raspberry Pis on the space station at the moment. And as a STEM ambassador, I think that's dead cool because if you want to get kids to start programming, tell them you can do it in space. In fact, anybody, I think. And that's exactly what you can do with the AstroPi project. They won't have you doing it in C# though, that'll be in Python, sorry. But even so. And then servos, which we'll need, and I'll talk about them. So, the circuit we'll be using is that, which isn't actually as complicated as perhaps it looks. So, controlling servos takes a little bit of power actually. So I've used this board you can see at the top. It's called a Servo 6 board, but you don't need one of those. It's just a nice, neat way of doing it. What it does is it allows you to be able to control the power, feed the power into these servos separately to what the control's doing from the Raspberry Pi, and that's what we've got here. So we've got various different pins connected for zoom in. We've got pin 25, which is ground. Now, if you do buy that Servo 6 board, don't make the same mistake I first made. That first pin is actually ground. When I looked at that pin numbering scheme across the top, I thought that was channel 1. And why is my channel 1 just not working? Because there's no ground. So that's what that pin is doing. And then we've got pin 35, pin 13, and pin 12. And these are all connected to the various different pins on the Pi. But what's interesting is there's only 2 what's called hardware PWM channels on there. And I've got 3. So we need to solve that problem, and you'll see how we do that in a bit. And then on the other side of that Servo 6, we've got these servos. Now, these are what's called 9G servos. They're just dead cheap. You can buy them from Amazon for pennies. It kind of does mean they're not all the same, and I'll talk a little bit about that. But for the most part, the colouring of the pins on there will be pretty similar, but there might be orange and brown like I've got instead of yellow and red, but you know, you'll figure that part out. You can't really blow these things up. You plug them in wrong, they just don't work, so it's fine. You'll see that on this board we've got a little C. It's hard to see, but the far left hand of those pins is the control pin, and the other 2 are just power. So they're 5 volts these things are running on, so pretty easy to hook up. That's the control, the power, and the ground. So servos, these are basically little motors, but they use something called PWM, or pulse width modulation. And that is a bit more complicated than I'm about to explain, but this is the basics of it. So if you imagine you've got pulses that are small with a big gap in between, the servo will go one way. And the servos I'm using have got 180 degrees of freedom. You can get 360-degree servos, but all of the wires would get all tangled up in my robot arm if I did that, so don't want to do that. If you imagine then you've got medium-sized pulses with a medium-sized gap in between, the servo will go the other way, and then a big pulse with a little gap in between, and the servo will go the other way. They're actually floating in that position normally, and you can kind of hear it sometimes because it's buzzing, and they're fixed. They won't let you move them without breaking it, that is. But this is pulse width modulation, so that's how these things are working. And that device bindings library, that gives us a bit more control over that. PWM, that comes as part of the GPIO NuGet package, so you can do it on your own, but just use somebody else's code, and you'll see that as I go through. So let's make that work, which is essentially going to make my robot arm dance around, if it works. So let's switch to that branch. And I'll take you through what that's doing. So we've still got the GPIO, and we've still got threading at the top. But next we've pulled in PWM from that GPIO, from that device library. So that's the basic PWM and the drivers. But then we're using the device bindings NuGet package, and we're grabbing a servo motor from in there. You've got to send frequencies, essentially, to get this thing to work. And it's just easier if you can just tell it the angle you want to go to. So it's really wrapping a bunch of that control for you. Scrolling down, we've got Hello World, as you'd imagine. And the next thing we're doing is creating a PWM channel and we pass in the chip number, the channel number, and then a frequency just here. There's only one PWM chip on the Raspberry Pi, so both of these are 0 for both of these PWM channels. And then there's 2 channels on that chip, so 0 and 1. And these are the hardware ones. Now, the reason I mentioned that earlier is that you imagine those frequencies have got to be pretty stable. Otherwise, this thing's going to be jittering all over the place. And if you've ever tried to do timing in .NET, it's actually quite hard to get specific timing to work, which is a problem that was solved again with this device binding library, which took me a while to figure out, actually. So there's only 2 hardware channels. You need a software channel. And if you've got any software timing, you've got the operating system and interrupts and all sorts of stuff that's happening that ruins it. But again, we can create a software PWM channel. We tell it the pin that we've connected to, and that's pin 27 in this case. Same frequency, and then, don't remember what that 0.5 is, but just leave that as it is. But this is the important part just here. We've got true, and that is essentially telling it to go into a high accuracy timer mode. And I had to message them to figure this out, and I felt stupid afterwards. But it wasn't in the docs, so I don't feel that stupid. But just adding a true fixed my problems, because I did this without it, and oh geez, it was terrible. But still, it was a learning moment. So once you've created your PWM channels here, you just create a servo motor from that device binding. You pass in your PWM channel. You tell it how many degrees of freedom your PWM-driven servo motor's got, and in our case, 180. And then a minimum and a maximum frequency. These are the ones that you might have to change, because they're going to determine how far this thing will go between 0 and 180 degrees. And yeah, they're pennies on Amazon, so repeatability is probably quite low. So just bear that in mind. If it doesn't go all the way, that's probably what you need to change. And I did change it for the software one because the timing's slightly different because of how it's done. But you can see I'll just pass in that PWM channel, and it's the same here for the software PWM channel. I'll just pass it in. It's exactly the same servo motor, it's just now using a software PWM channel. Then I start my PWM-driven servo motors up, and then here's where I dance my code around. These are actually using a tiny little routine down here. It just makes my code a little bit better to look at. So we've got a servo, and we write an angle of whatever angle we want to run. So 3 different servo motors, and it's just going backwards and forwards between them, between some different angles. So there's not much to that code, but if you wanted to write it all yourself and control the PWM yourself, it would be a bit more complicated than that. So that gives you the idea of what that's doing. So let's run that, and hope this runs. I'll put the batteries in, that's nearly always my failure. Oh, there we go. Yeah. So we've got what I've called a rotation, and then we've got what I've called a reach, and then I've got a grab. So it's exercising all 3 of those. But actually this is cool now. We've got a Raspberry Pi C# controlled robot arm working there. So that's a bit of a step up from Hello World. But we've not had to go that far. The code wasn't that complicated, really. I know there was more of it, but there was a lot of repeated steps in there. So that's cool. I like that. Well, thank you. And I could just stop then, but that would be really boring. When I got to this point, when I was, because I mean, this was just me geeking out. I wasn't intending to do a talk when I was doing this, but I wanted a way to be able to control that thing in real time. And there was a million different ways of doing that. But I thought, if I make a web app, then that gives me a little bit more flexibility. If you've ever seen any of the stuff I do, I'm nearly always talking about IoT hubs and Azure and stuff like that. You could do this with IoT hubs, but it wouldn't be real time by any stretch of the imagination, so I didn't do that. So I'll show you what I did do instead. So we're going to create a Blazor app, and we're going to use something called SignalR, and I'll go through both of those now. So if you've not used Blazor before, which I'd be surprised, or even if you've heard of it, surely you have, then it was just designed as a single-page framework to go with those other 600,000 JavaScript versions. But what's great is that you do all this in .NET rather than JavaScript, which you could argue why, but if you've got a C# dev house, this is great. You don't now need JavaScript devs as well as .NET devs. It was actually created by this guy, another Brit, Steve Sanderson. Some say he just created it as a bit of fun. and he went to a Microsoft conference and demoed it, and then they jumped on him and decided that this was the next big thing. And yeah, as I say, it replaces the JavaScript with C#. There's a few different versions of it, and I've only mentioned the two big ones here. There's server-side and client-side. So server-side is all up in the server, as the name would tell you. And what it does, it uses SignalR under the hood to deliver DOM changes down to a thin client that's running on your browser. And then the interactivity goes back up the other way with SignalR as well. And that's great if code security is something that's high on your list, because now you're not delivering your entire code base down onto somebody's browser. It's all just running in the client, in the server, and keeps it away from prying eyes, which is quite useful. But then there's client-side WebAssembly as well, and that's a reasonably big buzzword. And that's going to be running what is essentially a VM in your client, in your browser, and that pulls down actual full-fat .NET Framework DLLs and runs them in that VM. There is going to be a proper version of WebAssembly, if not already, but that is the version that I'm demoing. And actually, I'm demoing an amalgamation of these two, and when I talk about SignalR and show you the code, you'll see why. But it's plugin-less, so not like Silverlight. Sorry, Silverlight. And it's supported in most modern browsers, but you know, it's now a different day, and I don't know what Safari's doing. So, and then SignalR. So this has actually been around a while, but it allows you to have real-time communications between multiple clients. It was created by these two clever chaps, David Fowler and Damien Edwards, way back in 2011. So as I say, it's been around quite a long time now. And it enables this bidirectional communication support, which is what I wanted. I wanted this real-time link between something and my Raspberry Pi robot arm. At the top end, it'll support WebSockets, but if you can't get that to work because you've blocked ports, then it will drop down all the way to long polling. I've never needed to do that. But actually, we'll see some issues along this line with SignalR in a bit, and I'll ask you a question and you'll get peak points if you can get it right. So let's drive it with something a bit more interesting. So I am going to switch my code right back up into main, and I also need the IP address of my machine, which I think should be this one. So what we're going to be doing is connecting the Raspberry Pi to a web app that's running on my PC here. So, and it's still sort of, every now and again when I'm doing this, it throws me. So the Raspberry Pi needs to connect over what is my hotspot on my phone so that I can get these things to talk to each other, because God knows if I could do that with a conference Wi-Fi. And then it's just going to connect to the SignalR service that's running on my machine here. And that's assuming, tell you what, should we be intelligent and just double check that I've got the right IP address? It's not hard. Just in case it's disconnected and reconnected since. 192.83. Sounds about right. 192.83. So that's good. So I'm going to run that. I saved it right. So that's just going to, I'll go through the code, but that's just going to sit there and wait now. Just wanted to get that running first. Good, didn't crash. So, all of this is pretty much the same as far as the servo control's concerned, but we're going to bring in the SignalR client now, and HTTP, because that's how this thing's working. And then we create a hub connection. So this is a connection from the Raspberry Pi to my machine. So it's going to be communicating through what's called a SignalR hub. And then all the same stuff with the PWM and the servos. Nothing changed there. Next up, we create the SignalR connection using the hub connection builder. You'll notice that I've got some code down at the bottom down here. I'm connecting over HTTPS, and I had some issues trying to get the Pi to trust the certificates on my machine. I tried a bunch of stuff and it didn't work. But it turns out that you can do this dangerous thing, look, and accept any server certificate. Don't do this. Or do it, you know, and then tell me about it afterwards. but at least it lets it connect. You wouldn't normally need to do that. Just fix the problem. We can automatically reconnect if this drops out. This sort of works. It's not bad. And then we can build that connection and connect to the SignalR service running on this machine. Now, has anybody done a SignalR before? What was the first thing you did with it?
It's like 2015.
Yeah. What was your tutorial you followed? What did it make?
We were just trying to send random messages, I think.
Right.
Anything to,
Interesting. Nearly always a tutorial is a chat app, because that's a really good demonstration of how this thing works. So that's what I've usurped to show this. And I could have done it anyway, but I wanted to show that there's not far from a tutorial to get to something useful. So you'll see here that I've got receive message and I've got user and message. And this is what you'll see in a chat app. So you imagine you've got, a send and a receive window, and you can type and it'll appear on somebody else's chat. And it's the standard SignalR tutorial that you'll follow if you go and have a look at this. And again, I could have done this a bit more cleverly, but I want to show that this isn't too hard to do, actually. So the user, in my case, is which servo I want to control, and the message is the angle I want it to go to. So this is the same move to angle routine that I've got down here, and I'm just passing in the servo and the angle, and that just made this code look a little bit better when I was doing it, so that's why that's there. So we move our servo mode to 1, and we move it to the angle that we send as a message. And then we write that out to the console, and then we start that connection up, and off we go. So that piece of code there on the Pi is actually quite simple. And here, I've got the code that we've got on our web app. So actually, I'll show you the web app. That's this on the left-hand side. So I've just got 3 sliders. I could zoom in a little bit, but yeah, you can see what it is, those 3 sliders. And they're going to control the rotation, the reach, and the grab. And we can see that in the code. So I was actually using this mat slider library, this package of controls that you can get. These are open source libraries. What's great about Blazor is the community side of it. It's awesome. So you can get all sorts of different nice Blazor controls that other people have created for you. I'm going to zoom in just a little bit more. It's probably still a bit small. Let's do 200 and blow your mind. There we go. So these are pretty simple, but if you've never done Blazor before, these are razor pages, essentially. It's the same sort of idea that you get in ASP. So you can bind the value of a control, and that's what I've done here. So in a minute, I'll show you, but this is a property that I'm binding that to. And then we've got a min value of 0 and a max value of 180, because they're the degrees of freedom that our servo's got. And then a bunch of other stuff on the right-hand side, which we don't need to worry too much about. And I've got 3 of them, 3 different servos. And then, because this was a chat app, we've got the list of messages, but actually it's quite useful to see what angle you're moving those servos to. Next up, we've got a bunch of code here, which is very similar to what's on the Raspberry Pi, because I've created this in a way that is going to be like that. So you remember I've got a server-side version and a client-side version. Well, this is the client-side version, and this is going to be connecting the exact same way that the Raspberry Pi does to the SignalR hub that's living in the server-side version, and I'll show you that in a second as well. But we create a hub connection, and then we've also got our list of messages. But here we create our new hub connection, and we don't need to worry too much about IPs because it's on the same machine. But we connect to what is the chat hub, and I'll show you that in a sec. The same automatic reconnect and build, and then that same receive message that we saw on the Pi that just echoes out the list of messages that have been sent. You can detect if this is connected and do some other stuff if you want. I've not done that, but at least I've shown that you can. And then we've got our properties here, the 3 different servos. And every time that slider changes, it will update this property. And then we've got the hub connection that we created above, and we send a message called send message, which I'll show you in a second. And we pass in which servo it is and the value. So pretty simple. We do that for those other 3 properties as well. And then we just default to some random angles. The chat hub, this is all just by convention. So this is on the server side. And we can see actually if I zoom in a little bit, you can see that we've got oh, I can't do that. We can see we've got a client and a server, and then a shared, and that's for any shared business logic that you're going to need to use, but I've not got any of that. Actually, if we zoom in here, then we can see this is where our chat hub is. It just lives in hubs and chat hub. And actually, there's not that much to worry about. The code is dead simple. If we receive that send message, which is what we're sending from our client, then all of the connected clients, we send that received message along with which servo and which angle. So it's just repeating what it is, essentially, but every client that connects will get this message. So not particularly complicated. Setting up SignalR in Blazor, you've got a few things you need to do. You need to add SignalR into it, which is pretty obvious. And then you'll need to map the hub down here as well. So, and that's just mapping to that chat hub file that I showed you there a second ago. Not much to get that particular piece working. And this is all running. So in theory, if I move my servos, then we can see my robot arm moving. Now, you can see how it's nice and smooth. When we get to the next demo, it won't be that way. And I'll leave it with you to try and figure out why that might be. My little wobbly robot arm. But now we've got real-time control over the servos that are controlling that robot arm. So again, I could stop at that point, but I'm not going to, because that would be boring. But I like that. And I mean, it might seem silly, but I mean, if you think about it, you could use this, not this, but a version of this for medical. So you imagine you've got a surgeon in one state, he can control a robot arm in another state in almost real time. And that's being done. And in fact, they're even talking about doing this between here and the space station, so that you can have trained folk down here operating stuff on the space station in real time. And over with us, Kevin Bacon does an advert for our EE telephone network where he's shaving a celebrity from one side of the planet to the other side of the planet. I wouldn't do any of those things with this. Not on myself, anyway, you understand. So, yeah, so that's that little bit. I like that. But we don't want to stop there. So I'm going to stop my code. And I'm going to talk a little bit about Unity. So what's great about all of this is it's all C#. And we can do that if we start talking about VR as well. So Unity is a cross-platform game engine. Does anybody use Unity? It's pretty cool, actually. It's come a long way. But we can integrate with Visual Studio and program for VR in C#, which is pretty cool. Created way back in 2002, so like SignalR, this is old tech now. And actually, that's the same time .NET was created. And it wasn't always as good as it is now. But yeah, C# and VR headsets. What don't you want? It's great. So let's see how that works. And also, we can have some audience participation at this point. Scan that QR code, and in a second, I will connect my Raspberry Pi to a web version of my app, which you'll see. Now, this will be jerky. And yeah, as I say, you'll get some peak points if you can tell me why that might be. And those folks who know Azure naming conventions might be able to work that out. That's just a little hint. So I need to change this IP address now to something which is a bit more sensible, which is this. All of that lot, and then run that up. Is that website working for those folks that have dialed in? Maybe no one dialed in, we might not be bothered. Oh yeah, that would help. There you go. Now this thing's not fastened down very well, so it gets quite funny because it just falls over. Only I don't know it's fallen over because I've got this thing on my head. Have you all got the QR code? Is that app working? Oh, somebody's moved it. See, it nearly fell over then. Be nice. Woo! Oh, there we go. Try not to rip all the wires out, yeah? Because it makes this next part of the demo not very interesting. Right. I'm going to go all the way across here. and hit this play. So, TV version of that same, oh, it nearly fell out. Oh, you're doing well, folks. I'm impressed. Normally this falls straight over. So, this is the part that's always hard, because I'm going to try and stream what I can see on here to that left-hand window, while also making sure that you don't do that. Ah, you buggers. You lost your points. So it's not massively smooth. Has anybody figured out why? Yes, exactly that. And I didn't figure that out until I was over here, and there was no way I was changing that before this talk. So jerky, you're gonna have to live with that. But it shows something in that SignalR is real time, but it can only deal with what it can deal with. Really, what you're gonna want is some form of geo redundancy, and then you're gonna have to work that out for yourself at that point. So, ooh, very good. Somebody saved it. Right. Anyway, enough chatting. Let's see. Do. Okay. Oh, it's there. You can see it. Right. I am going to maximize this, because some folks that are doing that will be able to actually see it. But this is my wobbly robot arm, and actually I can move it in here on the reach. I can even make this thing fall over, so you'll have to tell me if I do. And if you move it, I'll be able to see it move. So if you've still got that open, there you go. It's just about as wobbly in here as it is in real life. But you can see, once you've got SignalR set up, now you can control these things using anything that supports .NET, of course. So, I mean, I'm using a Raspberry Pi. We could do this, as I mentioned, with a small Arduino, like an ESP32, and the Nano framework, which, you know, you're more than welcome to do it. It might be a cheaper and easier way to do it. Or, you know, you could just do something fun like control it in VR. Because I always wanted to do that. I always wanted to make something like that. Actually, the hard part I found with this was getting the NuGet packages installed into the app. I think I did it the hard way after speaking to a couple of folks, but I don't know if you've ever, because NuGet packages are essentially a zip file, a cab file, actually. And have you ever extracted one of those and looked inside what's in there? You've got the DLLs for all the different architectures in there, and you need the specific one. It's having a rest on the VR headset, isn't it, friends? You're going to need the DLL specifically for the ARM chip that's in here. So you can't just put the NuGet package in there. You need those specific DLLs, which was really annoying, because now you're in DLL hell, because you've got dependency tree that goes on the back of that. So you download one and put it in there. Oh, it don't work, because I'm missing this DLL. It took me a long time, about half a day of just diving in, trying to figure out which DLLs are missing. I think there's a better way to do it. I hope to God there is, because that was awful. But that was the hardest thing I found. That robot arm, that's quite a new functionality that's been added to Unity. And you can just go ahead and grab that, and then you can start controlling it. Oh, look, let's run out of that. But anyway, that's the demo log. So all of those worked, which I think is a bloody accomplishment all on its own. But yeah, so that was cool. So it didn't always go smoothly for me. My cat, whenever I was playing with these servos, decided that she loved it, and she would jump up and play with them. And it was jerky as hell when I first started using it. So this was the software PWM problem I had. And you've seen for yourself that, you know, if you don't be careful and fasten these things down, then they just fall over. So yeah, but I like it falling over because it's fun, honest. So there's some links here. Don't worry too much about these, because I've got a link to the slides, which have got all these links in it. Some folks are playing with it, look. The first time I did this, actually, Shahid's out there, and he'd moved to New Zealand, and I was in the UK, and he dialed in just randomly, and he was moving this from New Zealand, so literally from the other side of the planet. I guess it would have been as jerky for him as it is for us just here. But yeah, so all of the code is in that GitHub repo. There's a slightly simpler version of the robot arm. This took me about, I don't know, 5-6 hours to build once I'd finished printing it. But my friend Cliff, his son has created a dead simple one. These servos They come with a couple of little screws, and all you need to do is print 4 3D printed parts, and you use the screws that come with the servos and screw it all together. Now you've got a 3D printed robot arm that's far easier to build, and that's in that same GitHub repo as well. If you want to find out about C# 9 and .NET 6, then you can go look at that there. Is this not C# 10 and .NET 6? Anyway. And then that next item down is a blog post, actually a series of blog posts on my site that will show you how to get this all installed, and then various other things, including connecting it up to Azure and making all of that lot work. A bit of information then about the GPIO NuGet package, but also the source code for the device bindings, which will give you all of the list of the devices that you can go and control with that NuGet package. And then, as I mentioned, there's the original 3D printed robot arm on Thingiverse. You can go find that, and then see if you can find all of these random different screws and bolts that you need to get that to work together. I didn't manage to find everything I wanted, but it works. And then there's a workshop version of this as well, where you can go through and build the code all up yourself as well, or take it and run it as a workshop if you're that interested. If you're interested in Blazor, go check that out. That's that map Blazor library, next one down. If you want a bit more, then you can go to the awesome Blazor site, and they list all of these open source community contributions in there. And then SignalR, and then I mentioned Uno platform. Really do, if you want to make GUI apps for a Raspberry Pi, then this is a really good way of doing it. Myself and Cliff Aegis and Maria Anastasia Mustaka will be resuming our Azure IoT live show. We do this on the Azure-ish Live channel, so there's a bunch of other shows that are on there as well. They're all paused because summer and stuff like that. But they'll be coming back, so do check that out. If you want to take your IoT to another level, I actually created the AZ220 Microsoft certification, along with a few other folks, and I've also created a bunch of Pluralsight content to help you pass that exam. Do definitely go and check that out, because it's pretty well aligned to the exam if you want to go and pass it. And then if you want to contact me, there's a bunch of places. At Pete_codes on Twitter is going to be the easiest place. You can try emailing me, but it's email, isn't it? I run a bunch of meetup groups as well, and these are all virtual at the moment. So I've got Knots IoT in the bottom left, .NET Knots and Knots Dev Workshop, which isn't running because that's a workshop-based thing in person only. And then a couple of others, but I'm also part of a podcast, the Agile Engineering Podcast, and that's that Azure-ish Live Twitch channel that I mentioned earlier. But the one you really want is that link to the slides, and if you want it even easier, then there's a QR code to grab that, and that'll have all of this in it as well. And that's about it. So by all means, ask your questions. And thanks for listening. Any questions? Any feedback? It was wobbly, man. Good. Wow. No questions. Must have done a good job explaining. Yeah, that one, a reasonable length of time, because there's a fair amount of layers in that. So I think it took about 6 hours. The one that I mentioned, though, that simple one, only take about 45 minutes. So definitely print that one, unless you want to make that one specifically. Yeah. And I've got an Ender 3D Pro, so it's all right. Maybe if you've got a Prusa, you could get that done faster. But yeah. Cool. Well, thank you very much for coming. Cheers.